preparing for my defense. Unlike some people, I have to prepare that I know everything in the manuscript that I wrote. My supervisor did a major correction regarding what been written, like expression, and it sounds like French translated to English. So now I have to actually know every word she wrote. I prepared the Beamer slide. I that will be another video, a full video. I will do a full video where I go. So now we will investigate the existence and uniqueness of the singular fractional snap boundary variable. In this chapter, we present the main novelty of our work, namely the existence of results for a singular Psi-Caputo boundary variable problem with non-periodic boundary conditions under suitable conditions guaranteeing the boundedness of the nonlinearity on candidate solution. This study was motivated by the analysis of the corresponding case, more precisely the paper 26, which is the non-singular. It is the only reference that my advisor gave me. Uh, 6, 7, 6, 7. Okay, let's continue. This study was motivated by the analysis of the corresponding non-singular case, more precisely the paper 26. Let's consider the following problem. This is the alpha C fractional derivative, Caputo derivative with respect to V is equal to V1, and the derivative of V1 equals to V2, derivative of V3 equals to a continuous function with parameters t, V1 had till V2, V3. It can be rewritten as the following. It can be rewritten as the following problem, where the third derivative, we apply a derivative with delta, then gamma, then beta, then alpha, which equals to a t, which is a continuous function with initial conditions with their boundary conditions, which they are non-periodic because the lambda here, lambda 0, lambda 1, lambda 3, lambda 0, lambda 1, lambda 2, lambda 3 are in the real parts, but they do not equal 1. Our study is devoted to the singular fractional snap boundary value problem, where the nonlinear term becomes singular near the origin. To overcome this difficulty, additional assumptions are imposed in order to ensure the possibility and the boundedness of the solution. We will do some preliminaries. In this section, we introduce basic definition, notation, and primary results that will be used throughout this chapter. We also recall several concepts and provide the fractional calculus in the G-Caputo sense, and essential for and they are essential for our analysis. Singularity theory. What do you mean by singularity here? We mean that an operator T is continuous except for a function, a set S that has the measure 0, and the function is equal to e to the power of minus u. This minus u is in the interval 0, 1. So this, when the u tends to 0, the function goes to infinity, and that's why we call it singular here, because it tends to infinity, but it's still locally integrable near the origin. This property plays a fundamental role to ensure that the associated integer operators are well defined. Crucial definitions. We will define this operator derivative with respect to psi, which equals 1 over psi, the derivative of psi, times the normal operator derivative. The case C integral, and for an integrable function y takes value from t1 to t2 to the real set, real number set to R. With respect to psi is illustrated as follows. The t integral is equals to this, and where it's gamma function, it is the gamma function, it is the interval from 0 to infinity, e to the power minus t, times t to the power of k minus 1 dt, where t is greater than 0. Another definition, we would define the case fractional derivative of y, which is defined by, we compute through this two operators, the operators that we defined earlier, with the integral, the case fractional integral, and we get the 1 over gamma of n minus k times the operator to the power n times, we apply the operator n times, to the integral from t1 to t psi of t minus psi of zeta to the power of n minus k minus 1 times psi prime y zeta d zeta, in which n is equal to sine, it's equals to sine of k plus 1, or the floor. It is sine The function sign takes the nearest or takes the nearest normal and normal number. The case C Caputo derivative of y is defined by the case of Caputo derivative of y. The case C Caputo derivative of y equals to n minus k C integral times the operator that we defined earlier to the power of n of y, in which n equals to the sine of k plus 1 for k is the not in the if for k not in the normal number, but it equals to k for k is in n. In other words, the case C Caputo derivative of y is equal to the operator that we defined earlier with respect to y if case equals to n and equals to this expression if k is not in n, not a normal number. This is the diagram. The problem with this diagram that we are using v instead of y because we change the parameters many times, like the c equals 3, then we change it to c, then the v it was mass frac v, then we changed it to v, then we changed it to y. Yeah. This is lemma 1 and lemma 2. Lemma 1 and lemma 2 are lemmas that we need to use to get the integral Volterra equation. And then we should be having a Banach space. The Banach space that we will use is this Banach space that where y is in the continuous space, and the derivative of y and the second derivative and third derivative are also in the continuous space. The norm that we will use is y equals to the step norm of y1 and this step norm of y2, sorry, step norm of y3, step norm of y4. Yeah. The problem formulation. In this section, we present the mathematical fundamental formulation of the problem under consideration and introduce corresponding fractional framework. We extend the non-singular problem studied in the reference number 26, which is the to a singular case where the nonlinear term t exhibits a singularity growth. This is the problem that we are using. The alpha c caputo derivative of y equals to y1 is the beta c caputo of y2 equals to y1 to equals to y2 is the delta, the gamma c caputo derivative of y2 equals to y3, and the delta c caputo derivative of y3 equals to a function t that is corresponds with that takes parameters are the parameters of this function are the time and the all the functions y1 to y2 y3 and so on. The subject to the non-periodic conditions are non-periodic conditions are y of t1 equals to lambda 0 of t y of t2 or y of t1 equals to lambda y t2 and so on. Then the analog condition for the higher order derivative with parameters lambda 0, lambda 1, lambda 2, lambda 3 are in the r plus except 1. Here the parameters alpha, beta, gamma and delta are in they are between 0, 1 and the psi function is continuous and its first derivative is also continuous and it is strictly increasing with the derivative of c doesn't equal to 0. So how are we going to integrate and prove the existence and uniqueness of the solution of a singular term? How are we going to introduce a Volterra equation with a kernel that admits singularity? This is the question. We all know that the Volterra equations require the care of the Volterra equations. It has to be continuous, and to obtain the solution we have to integrate this term that admits singularity. We want to integrate infinity here. That's the ridiculous goal I set for myself, to introduce a Volterra equation with a kernel that admits a singularity, that it is not even admits singularity. My first idea was like it have to be a place. The Volterra equations have to be. We have to get rid of the continuity condition to the kernel. So the kernel have to be non-continuous. And this is nearly impossible to do. The kernel of the Volterra equations, it have to be continuous. but I said that I extended to singular place, singular case. This T admits singularity. I put some hypotheses that will be useful. The hypothesis for the following assumption we will use to establish the existence and uniqueness results are the singular problem. For the singular problem, the first hypothesis is the continuity. All inverse fractional derivatives appearing in the system are continuous, are continuously differentiable real values in the function t1, t2. So I'm not talking to the t here, I'm talking to t1, t2, t3. They have to be continuous, and they have to be not only continuous, are continuously differentiable real valued function on t1, t2. The second hypothesis, I call it singular growth. The function is in the continuous space except for a set here. This set uh, contains points that are of measure 0, but if they take the value on this set, it becomes, it blow up, basically. That's what I'm saying. So T is in the continuous set except for S. S here is a Lipschitz measure 0 set containing the origin and satisfying that T is bounded, and T is bounded by function A and B for all T1, T2 are in the interval. T1 is the interval, T is in the interval T1, T2. U, Y1, Y2, Y3 are in the set of R4 except S, which is a set measure 0 set containing the origin, where mu, v, q, delta, sigma are in the interval 0, 1. Theta is the maximum, has a maximum of, is the maximum of these parameters, and it is strictly less than 1. Alpha, beta are in the L infinity. Remark, the boundedness of the function a, b is essential to control the growth of the nonlinear term and to increase that the associated integer operator is well defined and bounded on the underlying function. I needed another hypothesis, which is the positive of the singular lower bound. There exists a constant k and a constant m greater than the 0 such that t of t, u, y1, y2, y3 are greater than k times mu to the power of minus mu, y1 to the power of to v, y2 to the power of rho, y3 to the power of minus sigma minus n. These conditions guarantees the preciseness of the singular structures and ensures that the nonlinear terms exhibit a sufficiently strong growth near the singular point. The third, fourth Lipschitz condition, my fourth Lipschitz, which I really don't like it. I think it weakens my case. I mean, I get rid of a lot of things by introducing the singular growth and also introduce the positive lower bound. I think I've done enough. Like, I erased many things, and adding the Lipschitz conditions, it is a powerful thing because the logarithmic may or may not have Lipschitz conditions. This hypothesis is required to establish the uniqueness of the solution and Ohlm-Heier stability. There exists a constant L such that for almost everywhere t in the continuous in the interval t1, t2, and for all x, y in in the real valued therefore it is Lipschitz. T y x t minus t y y is less than L b of t y minus x minus y in the norm of L4, where b is L infinity. I need a coffee. I will have some coffee and then we into novelty. These are the hypotheses. Now we will see the how are we going to use the hypothesis to first have a Voltaire equation that admits a singular point that blows up. How are we going to do it? I mean the hypothesis, the singular growth hypothesis, it makes things easier because we know that the t is controlled by a and b in the continuous in L infinity. We will do that in the next live stream because I'm tired.